We just learned how to calculate the basic steps of one-way analysis of variance, which entails partitioning our variability in our data in terms of that between groups and that within groups, and then also calculating this measure of overall variability. And the key component of analysis of variance is this ratio of the mean squares between over the mean squares within. At this point, let's go through the steps for hypothesis testing for one-way analysis of variance. There are preliminaries as usual. You want to state the target population. You want to state the parameters of interest. So with one-way analysis of variance, you're interested in comparing these different group means. And then you want to consider the required conditions that we had discussed earlier. Then you move on to these 5 steps. You state the null alternative in terms of H naught and H alpha. You select a significance level, alpha, as usual. Then what you do is you compute the F test statistic, or the F ratio, which is the mean square between divided by the mean square within. For step 4, you assume that null to be true. You assume that all these population means are equal. And then you make a decision by either comparing the F test statistic with a critical value, or you calculate the probability or p-value, and you compare that p-value with the significance level alpha. And then, of course, you state your conclusion. So let's go through these steps. Step 1 should be familiar by now. You state the hypotheses. Analysis of variance, it's based on analyzing the variances, partitioning the variability in our data set in terms of that within and between groups. But the focus is on comparing means. So the null and alternative hypotheses are in terms of means. The null is just that all the observations come from the same population, while the alternative is that they do not. So the null we can visualize this way. All population means are equal because they come from the same population. Again, with one-way analysis of variance, we're assuming that the distribution in the population for each group is normal, it's mound-shaped, and we're also assuming that the variance, or the spread, within each group is the same in the population. So the null is that all population means are equal. The alternative is that these population means are not equal. They differ from each other. For step 2, we choose a significance level. We're going to use this level of alpha 0.05. For step 3, we compute the F ratio, or F test statistic. Typically, we'll use statistical software, especially when we have larger data sets. But again, you really should calculate this by hand at least a couple of times so that you understand it using smaller data sets. The F ratio is simply the mean square between divided by the mean square within. There are 6 steps that we use to calculate the F ratio that we just discussed. I'm going to review these just so that it's clear that this comes from our data, and this comes from partitioning the variability in our data set. We find the overall mean, sometimes called the grand mean, and then we find the group means, sometimes called the conditional means. These are the benchmarks by which we calculate the total sum of squares, the mean squares between, and the mean squares within. Then for step 2, we calculate the total sum of squares, then we calculate the within sum of squares, and the between sum of squares. Once we have these sum of squares, we divide each by the respective degrees of freedom, so we have the total between and within mean squares. Then we divide the mean squares between by the mean squares within. That's the F ratio, and that gives us an idea of the extent to which our data cluster around these groups. Again, if the mean square between is relatively larger than mean square within, meaning if the F ratio is really large, that suggests most of our variability is in terms of differences across groups rather than between individuals within groups, right? I'll repeat that again. If the F ratio is very large, it suggests that more of our variability is across groups rather than within each group. The F test statistic, or the F ratio, it lies on a probability distribution, which we call the F distribution model. This is just like what we've talked about before in terms of the t test statistic. It lies on the t distribution. The chi-squared test statistic lies on the chi-squared distribution. Well, we have something called the F distribution model. This is just a theoretical probability distribution that we use to make statistical inferences. The F distribution, it varies depending on the degrees of freedom between and the degrees of freedom within. where the degrees of freedom between is, as we've discussed before, simply the number of groups minus 1, and the degrees of freedom within is the number of observations minus the number of groups. In our notation, we typically refer to the number of groups as k and the number of observations as n. In essence, the F distribution is a function of the amount of information we have independently for those between groups and those within groups. The sort of shape of the F distribution model, it varies quite a bit depending on these two degrees of freedom. But it's positive or 0, meaning the F distribution model, it ranges from 0 to positive infinity. That should make sense, because the way we've calculated the mean squares between and the mean squares within, that ratio, it's not going to be negative. Right? You're always going to have positive variability, or at the worst case scenario, you're going to have 0 variability. But it's always going to be 0 to positive infinity. It's called the F distribution model because it was invented by a statistician who wanted to name a distribution after one of the founders of statistics, R.A. Fisher. So Fisher, his last name begins with the letter F, and this statistician thought, okay, I'll honor Fisher by calling this the F distribution. That's how you know you've made it in statistics, when you have a distribution named after you. Let's look at the varieties of the F distribution model. We can use statistical software to examine how this probability distribution changes depending on the number of degrees of freedom between and the number of degrees of freedom within groups. Again, these degrees of freedom, they just reflect the number of groups we have and the number of individuals, or the total sample size we have. And you can see the distribution changes a bit, right? We use this probability distribution and the F ratio to make inferences. We can compare this F test statistic with some critical value. In that particular route, if this F test statistic is greater than or equal to the critical value, then we can reject the null, that all the means in the population are equal. The null hypothesis implies that the F ratio equals 1, right? That the mean squares between equals the mean squares within. We calculate this critical value, which we call F subscript alpha. We can use tables, but we will typically use statistical software. And again, the critical value, F alpha, depends on the level of alpha, but also depends on the degrees of freedom, both between and within sum of squares. Right? A minor technical note is that although the one-way analysis of variance, it's a two-sided alternative, the rejection region in our probability distribution is only the right-hand tail. This is just like the chi-square distribution. That's because we only can get positive values from our F ratio. So let's look at this. Right? If the basic goal here is that if our F test statistic that we obtained from our data, if it's greater than or equal to F alpha, then we're going to reject the null hypothesis. So if we set alpha to 0.05 using convention, we have a degrees of freedom of 2 and a degrees of freedom, degrees of freedom between of 2, and the degrees of freedom within is 9. So our critical value is going to be 4.26, and we can plot this. Right? This is what the F distribution model looks like with 2 degrees of freedom between and 9 degrees of freedom within. So 2 between, 9 within. We can see that that's our critical value, and then we have this rejection region. That's just the area under which, if our F test statistic lies in that region, then we can reject the null hypothesis. Right? So in our case, our F test statistic is off the charts. Right? The mean squares between divided by the mean squares within, it's over 38. Right? That's much larger than this critical value of 4.26. Therefore, we reject the null that these groups all come from the same population, that all of their population means are equal. Right? We can also calculate a probability or p-value using the significance level alpha. The p-value is simply the probability of an F ratio as more or extreme than the one we actually obtained. And we use the typical evaluation for interpreting a p-value. So if our probability value is less than or equal to alpha, our criterion level, then we're going to reject the null of equal population means. Typically, we will use statistical software to calculate these p-values. You could use tables. And again, even though the one-way ANOVA, it's a two-sided alternative test, the rejection region, it's going to only be in the right-hand tail. That's because the probability distribution ranges from 0 to positive infinity. The decision rule is that if the probability value is less than or equal to alpha, then we're going to reject the null hypothesis. So this is what the F distribution model looks like, with 2 degrees of freedom between and 9 degrees of freedom within. The null implies an F test statistic of 1. Right? If they're all from the same population, the mean squares between and the mean squares within, right, we'd expect them to be more or less the same. Our actual F test statistic is way over on the right-hand side. It's 38. The p-value, the probability of obtaining a test statistic as or more extreme than the one we obtained, it's almost 0, right? It's just going to be more to the right than 38.23. It's very unlikely that all these 3 groups come from the same population. So in general, we reject the null if the F ratio is considerably larger than 1, as a rule of thumb. If you reject the null, you can conclude that not all population means are equal. To put another way, you can say, well, if we're going to reject the null, you can say that they're not really from the same population. These are really distinct groups. If you fail to reject the null, then you can conclude that all means are from the same population. To put another way, they don't really differ from each other all that much in the population.